The Big Bang Theory first proposed the possible manner in which the universe originated and subsequently developed. The theory was proposed by Georges Lemaitre. According to the Big Bang Theory, the universe expanded from an extremely hot, dense phase in which all its components were sealed tightly. An explosion of this entity caused the components to expand, leading to the formation of the current observable universe.
Only a fraction of a second after the Big Bang, and the destiny of the universe is already mapped out. The sun burns because of forces forged more than 13 billion years ago. The stars and planets form from the way the universe rapidly expands. Science can trace everything we see today back to the first second of creation. But we're here because of what happens in the next few beats of Planck time. The universe is flooded with the building blocks of matter. So far on our cosmic clock, the early universe is nothing but energy. How did pure energy turn into matter? Everything around you is made of matter. What you're sitting on, the air you breathe, the whole planet is made of matter, and matter is made of atoms. And in the first second after the Big Bang, the ingredients for atoms are created. How matter appeared mystified scientists, until 1905, when Albert Einstein comes up with our most famous equation. E equals mc squared. Einstein's equation tells us that energy, E, and mass, m, are different forms of the same thing. Matter and energy are interchangeable. Some scientists later used this equation to create the most destructive weapon in history, the atomic bomb. It offers a clue to what happened in the first second. In a nuclear explosion, particles of matter are ripped apart to produce an enormous amount of energy. During the Big Bang, the exact opposite happens. An enormous amount of energy turns into matter. Einstein's equation prompts a conclusion. As the baby universe expands and cools, the pure energy of the Big Bang converts into the particles of matter that make us. A dense clump of matter formed in the center. It's called a protostar. At first, its heat was due to friction. But when the clump reached 18 million degrees Fahrenheit, nuclear fusion kicked in. 4.5 billion years ago, our star was born. Hydrogen atoms fuse together to form helium, and in the process, release photons. It's the first light made by our sun, and it will keep on shining for 4 billion years. A vast nuclear furnace nearly 1 million miles across. From a distance, this process seems almost peaceful, with the sun's power gently radiating out into the early solar system.
We had a pretty spectacular origin, I think.
Recent research suggests the solar system's birth was far from peaceful. Our sun may in fact have been born out of one of the most violent events in the cosmos: the explosive death of another star. And even before that, it seems there was an explosion so huge that it created an entire universe. The Big Bang. No one knows what caused it, but we think that the Bang created space, time, and all the matter in the universe.
The sun, in all its mesmerizing splendor. Our light, our lives. Everything we do is controlled by the sun, depends on it. And more than that, it's the Greek god Helios driving his chariot across the sky. The Egyptian god Ra, reborn every day. The summer solstice sun rising at Stonehenge. For millions of years, this was as close as it got to staring into the face of God. 150 million kilometers from home, a 20-year journey by plane. Switch it off, and it's so far away, we wouldn't know about it for a whole 8 minutes. It's so big, you could fit 1 million Earths inside it. So heavy, its gravity controls the entire solar system. But who needs numbers? We've got the real thing. We see it every day, a familiar face in our sky. Up close, it's unrecognizable. A turbulent sea of incandescent gas. The thermometer rises to over 5,000 degrees. Down in the core, it's got to be tens of millions of degrees.
Man has pursued the greatest scientific advancements to recently replicate the initial stage of the universe. For this purpose, the internationally acclaimed particle accelerator, the Large Hadron Collider, or LHC, was built by CERN, or the European Organization for Nuclear Research. In our demonstration, we intend to display its basic functionalities.
Insignificant though this bottle of compressed hydrogen gas looks, it marks the beginning of the world's largest and most powerful particle accelerator chain. These are protons and have a positive charge, enabling them to be accelerated by an electric field. Their journey to eventually take part in ultra-high energy collisions similar to those following the Big Bang can now begin. It's about to enter the booster, stage 2 of the rocket if you will. In order to maximise the intensity of the beam, the packet is divided up into 4, one for each of the booster's rings. Straight acceleration is now impractical, and the booster is circular, 157 metres in circumference. In order to accelerate the packets, they are repeatedly circulated, and the electric field is now pulsed, in the same way that you push a child on a swing each time they reach a certain point. Magnets exert a force on the passing protons at right angles to their direction of motion, and so powerful electromagnets are used to bend the beam of protons round the circle. The booster accelerates the protons up to 91.6% of the speed of light and squeezes them closer together. Recombining the packet from the 4 rings, it's then flung on into the proton synchrotron, by analogy stage 3 of our rocket. Let's just follow 2 such proton packets. The proton synchrotron is 628 meters in circumference, and they circulate for 1.2 seconds, reaching over 99.9% of the velocity of light. In short, the protons can't go faster, so they get heavier. The packets of protons are now channeled into stage 4, the superproton synchrotron, a huge ring 7 kilometers in circumference. Soon, the packets of protons will be energized sufficiently to be launched into the orbit of the gigantic Large Hadron Collider, or LHC, which lies between the Jura Mountains and the Alps, and straddles both France and Switzerland. Lying deep underground, it has a circumference of 27 kilometers. There are 2 vacuum pipes within the LHC, containing proton beams travelling in opposite directions. The counter-rotating beams cross over in the 4 detector caverns, where they can be made to collide. The energy of the collision is double that of the individual opposing protons, and it's the debris from these collisions that is tracked in the detectors. Now the protons are ready to collide in the detectors. A steering magnet finally brings them onto a collision course. The total energy of 2 protons colliding in the LHC is 14 tera electron volts, and reproduces similar states to moments after the Big Bang. Particle tracks from these collisions will be analysed by computers connected to the detectors, and it's hoped these tracks will give a new insight into the very birth of our universe, how our universe has evolved, what governs its behaviour today, and where it's going in the future.
As time began to burn, like a startling sign that fate had finally found me, and your voice was all I heard.